Welcome, everyone. I'm excited to kick off our presentation today on thermodynamics, an overview. This is the first slide, and I want to warmly welcome you all. Today, we'll explore the fundamental principles of thermodynamics, including key concepts and applications. I'll give you a brief overview of what we'll cover, from basic laws to real-world examples. So, let's get started and dive into the fascinating world of thermodynamics. Now, let's move on to the second slide, which focuses on internal energy, denoted as U in the context of chemistry. Internal energy is a fundamental concept because it encompasses all the energy contained within a system. This includes the kinetic energy of molecules moving around and the potential energy stored in chemical bonds. Essentially, it's the sum of all microscopic energies that make up the total energy of the system. Understanding internal energy helps us grasp how energy is stored and transferred during chemical reactions and physical processes. It's a key piece in the broader picture of thermodynamics, connecting how energy changes relate to temperature, work, and heat. So, as we proceed, keep in mind that internal energy is the baseline energy content of a system, and it's crucial for understanding energy conservation in chemistry. Let's dive into the topic of chemistry. Chemistry is really the foundation of understanding how substances interact and transform. It helps us grasp the composition of matter, from atoms and molecules to complex compounds. By understanding these basic building blocks, we can see how everything around us is connected. This slide highlights the importance of chemistry in many fields, from medicine to engineering, and even environmental science. It's about understanding the reactions and processes that make everything work. Recognizing these key points ties back to our overall theme of exploring how science impacts our daily lives and advances technology. So, as we move forward, keep in mind that chemistry isn't just about lab experiments. It's about understanding the world at a molecular level and applying that knowledge to solve real-world problems. Let's take a closer look at the current state of the system. When we talk about a system in thermodynamics, we're referring to a specific part of the universe that we choose to analyze. Understanding its state is crucial because it tells us the system's condition at any given moment. Now, within this framework, we often consider adiabatic systems. These are systems where no heat is exchanged with the surroundings, which simplifies many analyses and helps us focus on work interactions and internal energy changes. Next, let's consider the different types of systems. We have open, closed, and isolated systems, each defined by how they exchange energy and matter with their environment. Recognizing these types helps us determine the appropriate laws and equations to apply. Moving on, one of the foundational concepts in thermodynamics is the idea of state functions. These are properties that depend only on the current state of the system, not on how the system arrived there. Examples include pressure, temperature, and volume, key variables in our analyses. It's also important to understand the relationship between the system and the surroundings. The surroundings encompass everything outside the system with which it can interact, and the exchange of energy and matter between them defines the processes we're studying. Then there are specific thermodynamic terms that form the language of the field. Terms like work, heat, internal energy, and entropy. These help us quantify and describe the energy transformations taking place. Finally, all of this falls under the broader umbrella of thermodynamics, the branch of physics that deals with heat, work, and energy transfer. It's the foundational science that allows us to analyze and predict the behavior of physical systems in a wide range of applications, from engines to biological processes. The study of these energy transformations forms the core of thermodynamics. Essentially, thermodynamics is all about understanding how energy moves and changes from one form to another. For example, the chemical energy stored in substances can be converted into electrical energy, like in a dry cell or a galvanic cell. You might not think about it often, but this is how batteries power our devices. Similarly, chemical energy can be used to do mechanical work. Think about how fuel burns in an engine. This chemical energy is transformed into the motion that makes cars move. We also see chemical energy stored in molecules being released as heat during chemical reactions. When fuels like methane, cooking gas, or coal burn in air, they release heat energy. All these processes are interconnected and are studied under the umbrella of thermodynamics. It's the branch of science that looks at the quantitative relationships between heat and other forms of energy. So, whether it's producing electricity, powering engines, or releasing heat, thermodynamics helps us understand and predict these energy exchanges. Let's consider a simple example to understand the concepts of system and surroundings. Imagine we are studying a reaction between two substances, A and B, inside a beaker. In this case, the beaker with the reaction mixture is what we call the system. It's the part of the universe we're focusing on for our observations. Now, everything outside the beaker, the room where the beaker is kept, is what we refer to as the surroundings. The surroundings include everything else that is not part of the system. The boundary between the system and the surroundings can be real, like the walls of the beaker, or imaginary, such as a conceptual line drawn around the reaction mixture. When we talk about the universe in this context, it's made up of both the system and the surroundings combined. So, to clarify, the system is the specific part of the universe we're studying or observing, while the surroundings are everything else around it. Understanding this distinction helps us analyze how energy and matter transfer between the system and its environment, which is fundamental in thermodynamics and chemical reactions. In essence, the boundary separates what we are investigating from the rest of the universe, allowing us to focus our analysis effectively. Let's start by understanding the three main types of systems. First, we have the open system. In an open system, there is an exchange of both energy and matter with the surroundings. For example, think of an open beaker where reactions happen freely and substances can enter or leave. Moving on, the second type is the closed system. Here, matter doesn't exchange with the surroundings, but energy can still be transferred. An example would be a closed vessel made of conducting material, like a metal container, where heat can pass through but no matter enters or leaves. Finally, we have the isolated system. This type is completely self-contained, meaning there's no exchange of energy or matter at all. A common example is a thermos flask or any other insulated vessel designed to prevent any transfer, keeping everything inside entirely isolated. These distinctions are important because they help us understand how systems interact with their environment, which is fundamental in thermodynamics and energy studies. The state of a thermodynamic system is essentially described by its measurable or macroscopic, or bulk, properties. These are the properties we can observe and measure directly, which give us a clear picture of what's happening inside the system. For example, when we look at a gas, we typically describe its state by quoting properties like pressure, which tells us how much force the gas exerts on the container walls, volume, indicating how much space the gas occupies, temperature, which relates to the average kinetic energy of the molecules, and the amount of gas, often given as moles or N. These properties are fundamental because they allow us to characterize the system completely, without needing to know every detail about individual molecules. Connecting this to the overall theme, understanding these macroscopic properties helps us analyze and predict the behavior of thermodynamic systems in a practical and meaningful way. When we talk about path functions, we're referring to properties that depend on the specific route taken to go from one state to another. For example, think about properties like pressure, temperature, volume, or even internal energy, enthalpy, and entropy. These are key variables in thermodynamics. Now, the important thing to understand is that some properties are different. These are called state functions. What makes them special is that their values depend only on the initial and final states of the system, not on how you got from one to the other. So, whether you take a direct route or a complicated path, the change in a state function remains the same. This distinction between path functions and state functions is fundamental because it simplifies how we analyze and predict the behavior of thermodynamic systems. It allows us to focus on the properties at specific states rather than worrying about the process details. This concept ties into the overall theme of understanding system properties and their significance in thermodynamics. Let's take a look at slide 10. First, consider the bursting of a tire as an example of an adiabatic process. It happens so quickly that there's not enough time for heat to be exchanged with the surroundings. An adiabatic process, in general, is one where no heat transfer occurs between the system and its surroundings. The key here is the adiabatic wall, which is the boundary that prevents heat from flowing in or out. A system that is truly adiabatic doesn't allow heat exchange across its boundary. However, it can still undergo changes in energy through work done by or on the system. Now, let's compare this with an isolated system. An adiabatic system has no exchange of energy and matter with its surroundings, but it can still interact internally. Its internal energy can change due to work. In contrast, an isolated system has no transfer of energy or matter at all, not just heat, but anything across its boundaries. Because of that, energy is conserved in an isolated system, and its internal energy cannot change over time. So the main takeaway here is that an adiabatic system can change its internal energy through work, even though it doesn't exchange heat with the environment, whereas an isolated system remains completely unaffected in terms of energy transfer. Understanding this distinction helps us grasp how different thermodynamic processes operate, especially when analyzing real-world phenomena like the tire burst example or other rapid, heat-insensitive events. Let's talk about internal energy. Denoted as U, internal energy is essentially the total energy contained within a system. It includes all the microscopic forms of energy, such as the kinetic energy of molecules moving around and the potential energy from molecular interactions. This concept is fundamental because it helps us understand how energy is stored and transferred within a system. When we analyze processes like heating, cooling, or work done by the system, changes in internal energy are often at the core of our calculations. Remember, internal energy is a state function, meaning it depends only on the current state of the system, not how it got there. This makes it a powerful tool for predicting energy changes in thermodynamic processes. Throughout this presentation, understanding U will help us connect the dots between energy transfer, work, and heat, giving us a clearer picture of the energy dynamics at play. Now let's look at what can happen to matter within a system. Matter can enter or leave the system, which is an important consideration when analyzing energy changes. Additionally, work can be done on the system or by the system itself, depending on what's happening physically. Heat transfer is another key point. Heat can pass into the system or out of it, affecting its internal energy. When these processes occur, the internal energy of the system may change, and this change is represented by delta U, which equals the final internal energy minus the initial internal energy, or U2 minus U1. Remember, internal energy is a state function, meaning it depends only on the current state of the system, not how it got there. Because it's a state function, we can't determine the absolute value of U directly. Instead, we focus on the change, delta U. This change tells us how the internal energy has evolved during a process. Now, the total energy contained within a system is called its internal energy. It's made up of various forms of energy: kinetic energy from translational, vibrational, and rotational motions, potential energy, chemical energy, electrical energy, and mechanical energies, among others. Understanding internal energy is fundamental because it encompasses all these different energy forms within a system. It helps us analyze energy exchanges during processes, which is central to thermodynamics and the overall theme of energy analysis in systems. Let's look at how the change in internal energy works. The change, denoted as delta U, is simply the difference between the internal energy at state B and state A. So, delta U equals UB minus UA, and in an adiabatic process, this change is equal to the work done on the system, WAD. Now, if the temperature at state B, TB, is greater than at state A, TA, then the temperature change, delta T, is TB minus TA. This temperature change reflects the energy added or removed from the system. The internal energy at state B is represented as UB, which depends on that new temperature TB. Let's consider an example. If we do mechanical work, say around 1 kilojoule, by rotating a set of small paddles in the system, we are adding energy. This process moves the system into a new state, which we call the B state, with its corresponding temperature TB. Now, there are multiple ways to change the state of a system. One way is through work input or output, which can alter the internal energy. Remember, for an adiabatic system, where no heat is exchanged, the process involves just work and internal energy changes. Initially, the system is in state A with temperature TA, and its internal energy is UA when we perform work or change the conditions. The system transitions to state B, with its temperature TB and internal energy UB. Understanding these concepts is key, because they connect the idea of energy transfer through work and temperature changes, which are fundamental to analyzing thermodynamic systems and their behavior.